be. And I think we will start it only if you feel that there is some disturbance or voice is not coming, or if you have any question, probably you can either put your questions in the chat box so that we can, discuss those once we conclude on the presentation. Okay. And if I am not audible, then please let me know so that we can recheck it. Or I hope my screen is visible. Can somebody please revert on that?
Visible, sir.
Yeah, and my voice is also audible to you, right?
Right, sir.
Okay, so let's start it. So I actually uh, was willing to discuss on the radiant cooling system with you all, because even in our colleges we have been taught to the lecturers. This is my first opportunity where I am discussing some system with the lecturer actually, who is going to guide our future industry leaders, I would say. And it is very encouraging that some colleges is being taking initiative to understand what is happening in the industry. And the one more point I would like to really mention over here is we are really lagging in the manpower in this industry, because we are talking to many colleges to participate and encourage this so that majority of the students should be able to absorb this industry. So starting with our today's discussion, I would say we'll discuss
Yes.
mainly on the radiant cooling system. But before moving that, we will discuss why calculations are more important, because base of any building will start from the designing aspect of it. So we will see first that, and then probably the radiant cooling system. So when we see that radiant cooling system nowadays, we heard many times that newer technology has came, and we are willing to explore that newer technology. But does really our fundamentals are changed, or radiant cooling is a new technology? So to answer that, it is actually interactive, but since I am only delivering from my side, majority of the people will think that it is new technology. But whoever thought that yes, it is new, it is not new. These are old technology. This is typical example of Golconda Fort. If someone has visited this Golconda Fort in Hyderabad, then probably they'll come to know what is the radiant cooling system. In this fort, basically, the water is channelized from higher side to lower side, such a way that water will get distributed to these walls and canals and the other areas, so that whatever heat is coming from ambient or from the sun should be get absorbed into these walls. So this is the best example, and this proves that this is a not new technology, because whenever you visit any fort or any caves, then probably you'll understand those are being kept at constant temperature throughout the year. So that is the beauty of these buildings. But somehow in between, during final solutions or newer industry solutions or cooling, we somehow miss this concept what our ancestor were using that. But again, it is very encouraging. Last say 15 years we are working on this kind of projects to deliver. But the question remains, why these people were using the radiant cooling system, or why to use the radiant cooling system? So the answer to that is the water. Why water? Because if you see, normally water density is 1000, and the air density is 1.2. So if you divide that, probably the water is 832 times denser than the air. Similarly, it is having 4 times heat carrying capacity. And because of this difference of air and water, if you see, this is the typical comparison. If you compare air and water, because of this advantages of density, heat carrying capacity of 1 liter water is equivalent to, say, 3,300 liters of the air. And nowadays we all know that majority of the time we fight with the architects when we design newer buildings. The high building height or space in the building is so important that nobody will like to lose the volume or space. And because of this phenomena, water makes more potential use instead of air. Okay. Industry understands the language of airflow or CFM. So we have done some analysis on that. We try to compare it, say, if we have 30,000 square feet area to be cooled and load is, say, 100 ton, then probably it would require 40,000 CFM to cater that, and 40,000 CFM at, say, best optimum velocity of, say, 1000 RPM, it comes to 40 square foot area of duct cross sections. And instead of that, if we use water, it can be only 32 CFM. So you just can imagine the big difference between that. So this makes more potential to use water instead of air. Now, before we get into the design, we need to understand few concepts. And I think that this slide can be skipped as we all are the lecturers and we know the basic fundamentals, conduction, convection, and radiation. So this slide I would like to skip because we all know what is happening in this process. Again, I would like to repeat that conduction is between the component, like handle is a solid component and there heat is being transferred, that is conduction. And in water it is being transferred from molecule to molecule and it is moving there, so it is convection. And of course the temperature difference created between burner and the pot, and because of that temperature difference the radiation is happening and pot is getting heat. So that is the basic concept of it. Now when it comes to radiant cooling systems basically work on radiation. So what is radiation? If we make some surface colder, like in this slide, if you see that the blue surface, which is floor, there we are supplying some water and the other side water is being drawn from that surface. So this surface is capable to gain heat from the different components. Like if we have any equipments like laptop, computers, so those heat. So because of that radiation, the heat can be removed from the conditioned area so that the temperature inside conditioned area can be maintained as per our desire. Similar, we have light or other equipments, maybe humans, or heat is being transferred through the structure. So all this can be removed by radiant. So because of this phenomena, this concept is called as a radiant cooling system. This is one thermal image. We took it from one of our project where radiant is executed. The left image shows the ceiling where the gypsum finish is given to the slab, and there inside that we have few panels where the radiant cooling system is done. You can just see from this, these panels are absorbing heat as it is at the lower temperature, and because of this heat absorption phenomena, we can feel the colder effect inside the conditioned area. Now, in any design processes, there are few steps that we will have to follow even before selecting any system. So what we do into that is the heat load calculation. I mean, we will have to make a calculation where we have to derive the loads, and based on those loads, we will have to calculate how much load can be, catered through this radiant cooling system. And then if we have any balanced load, then we will have to see how we can remove that load from the building, and then equipment sizing. So we are going to see all these, processes step by step, and then we will see how radiant cooling system is designed. Now what is heat load? This is the phenomena where heat load means how much heat we need to add inside the conditioned area so that it can come to certain equilibrium as per the user's requirement. So this is the heat addition when it comes to heating. But when it comes to cooling, if we are expecting cooling, it means we are removing heat generated through different components or maybe structure. So that phenomena is called as an cooling. So heat additing, normally people call it cooling, means we are, adding cooling, but actually in concept, it is removing heat from the component. This slide I'll skip. So we all know that these are different material phases: solid to liquid, liquid to gas. This is typical slide where it shows that if we heat solid, then before going in liquid form, there is a heat fusion where it will try to change its phase and become a liquid. Similarly, there is a flat line when the liquid is becoming gas, there is heat latent of the evaporation. So this is typical image where it shows that how different materials are changing its phase. So why I have added this slide, because in future what is sensible and latent load. So to make it simple, I have added this slide. So component of heat loads. When we say that we are going to do the heat load calculation, it means the heating or cooling, whatever we do, like any process we follow, whether we'll have to cool or heat, we will have to calculate the thermal loads. Whatever thermal loads coming inside the building, we will have to measure it, and we'll have to place it at one place. Okay, whether the building is insulated or it's normal, whether it is floor, ceiling, roof, any pressure to be added, any internal loads, lighting, equipment, and occupancy. So all these loads needs to be calculated in different ways and place in one, I would say, at one place, and from there we will have to calculate the loads. So when we do the heating loads, that time what we will have to see is what is coming from building. Like if we are losing some heat, that heat we will have to measure, or we may lose, uh, heat from the wall, floor, windows, and if we are, you know, adding some air or infiltration is happening inside the building, so that those loads also we will have to calculate. Similarly, if we have cooling load, the process is reverse way, we will have to calculate what is being added inside the zone. We should be able to measure those and calculate what amount of heat needs to be removed from the conditioned area to make it in equilibrium. So this is cooling and heating. Now, when we do any load estimates, first we'll have to define step by step. We will have to define what are the loads and exact requirement of that particular area to be used as a conditioned area, and then we'll have to point out which loads are higher so that if we can compensate those loads or reduce those loads, probably it can stand for that building for next say 50 years. So load calculation is important, no doubt about it, but parallelly, if we can stop any load coming inside the building by maybe using some insulations or maybe taking lesser amount of fresh air, if we can figure out those points, then probably it is going to stay for say next 50 year with the building. So heat load is important, but reduction is also major concern in any heat load calculation, and that's what industry is missing today. Okay, so when we start designing any building, first we will have to see where that building is located, because the building design in US cannot be constructed in India, or simply if you design any building, say considering Nagpur weather, cannot be considered in Pune or vice versa, because the ambient at every position is different. Okay, that has to be taken in account when we do any heat load calculation. The first part where that building is located, what is its geographical condition, and how temperatures are varying inside that area. So that is major concern when we do any heat load calculation. Post that, once building is located at one point, we will have to define how building is expecting from air conditioning system. Like if you see, this is the typical chart given by ASHRAE. So this is the ASHRAE comfort standard. So if you see that there are two hatches made inside this. So these are the ASHRAE standards define that how people are comfortable with different clothings inside the conditioned area. And there is a overlap between these two that defines a specific zone where majority of the people are comfortable. Normally this concept is called predictive mean vote. I mean maximum vote, what condition we vote, those conditions are mentioned where there is a overlapping in the hatch. So that is the best condition to design any building. Okay. So once we define the building, weather and condition, we will have to see what is the use of that building, whether it is a hospital, whether it is a hotel, office area, or whether it is server like 24 by 7, or industrial area, or residence. So air conditioning system, when we do heat load calculation, it differs schedule. If we, just to throw an example, if we design air conditioning system considering 24 by 7 operating schedule, the load per than building, we say that same building is occupied for a certain duration, maybe office hours. Why this is happening? Because of flywheel effect. When system operates for 24 by 7, then the entire premises or wall or envelope gets cool and will settle to that envelope to reduce the loads. So the U value or the assembly, is there any disturbance? It is continuously saying needs to, I mean, started recording. Okay. So this is the uh, thing we need to consider. What is that building envelope? How it is made? What are different layers onto that? And then only we can calculate proper U value of that. And reciprocal of that is the resistance. So hit resistance of that building needs to be calculated so that we can calculate how much heat is being passed through this component. Similarly, the glazings. Nowadays, if you see that there are 100 type of glazing, there are three main: single, double, and triple, and it is divided with certain spacing. There are nitrogens, layers, those are different things are used to stop the heat transferring from one layer to other. And even in single, double or single pane or triple pane, there are hundred of varieties, different manufacturers. So whenever we design a building, we need to have a specific data of that glass so that in future our heat load calculation will not get wrong while operating the buildings. So glazing is equally important. Similarly, building envelope. So when we see that heat needs to be stopped, if you see the gentleman is standing on the building and installing some insulation, which is the overdeck insulation in the building. So first I will explain you how important is the insulation, because ultimately it is stopping heat transfer from the out to in. So it is always better to cover insulation outside the building, because once we absorb some heat in the structure and then we are stopping is not a good solution. So it is better to stop at the outside only, so that building load will be limited even with same insulation. If you install same insulation inside the building, then the load is different, and if you install same insulation outside the building, then the loads are different. So these are very minor, small component, but it can show a different results in the heat load calculation when it comes to storage effect of that building. Similarly, post that we will have to see the building shadings, because uh, after selecting all good glass, good component, still we want some lights to be entered inside the building so that we should be able to use lesser amount of lighting inside the building. But similarly, we designed the different kind of shading components in the building that has to be taken into account. If we have any curtains or any shading inside or outside the building, that needs to be taken into account so that our small load will get tackled and we will get the best optimum results when we do the heat load calculations. This is I explained during the first slide of heating and cooling, infiltration or exfiltration, because air is a major component of heat addition. So that we will have to see if it is calculated very specifically. Just to discuss slide, normally people feel that my doors are closed, my window is closed, why to consider infiltration or exfiltration. Even with brick wall, with plaster, it leaks the air or it absorbs the moisture. So those components, small components, needs to be taken into account when we do the heat load calculations. So there are specific standards which now ASHRAE is being defining for considering the fresh air inside the building. So these two images are added, how person is comfortable when there is good ventilation or good indoor air quality versus the person sitting in very bad indoor air quality. So it should not be very high pressure or it should not be very low pressure. We will have to modulate in proper manner so that we should be able to maintain a desired indoor air quality. Similarly, lighting loads or internal gains. When it comes to internal lighting loads, we all know that we used to use that filament light in 15-20 years back, but we have now moved to CFL, and post that now we are using the LED lights. Similarly, different kind of equipments are there like computer, laptop, printer, maybe some designing differently designed equipments, or pharma industry equipments or industrial equipments, maybe refrigerators and blah blah. There are 100 kind of equipments. The hit load calculations or hitting of those equipments has to be considered very precisely, because if we are wrong in designing, or if we fail to calculate those loads wrongly, then probably it will affect on maintaining the relative humidity when it comes to critical areas. So internal gains are very much important to precisely calculate it, or otherwise it will gain consuming more energy to maintain similar air conditioning or similar condition inside the air conditioned area. Similarly, there are few latent loads like person, or maybe some cooking, or maybe some fountain, or maybe water flow, and things needs to be considered. Similarly, we see that occupants, but occupants are performing in different manner when it comes to their activity load. Like if person is sleeping, the loads are different. The person is walking, the loads are different. So these loads needs to be taken care into design very carefully. This is just to show how person load is changing when the he stands in different environments. So what we discuss is these are the different loads when it comes to cooling. Like whatever slides we discuss, this is summarizing. So any heat load calculation, we should see all these equipment loads are placed at one point, so that our heat load calculations will be perfect. How to do that? Because scattering all those loads for 5 rooms, 2 rooms, it is okay, but we are being involved where thousands rooms are there. So what we do in that is the data collection format. So this is the address, like how building is placed, what is the space number, what is the name of that area, what is the size, area, lighting, occupancy, equipment. So all these details we discuss can be jotted down in paper, so that when we do precisely heat load calculation, those are handy or ready with us. So this is one of the format. You can create your own format to do the heat load calculations and gather the data. Once that data is gathered, there are different methods of heat load calculation. One is manual and one is computerized. Manual is basically a CLTD method. If you go to ISRE website, there are few Excel sheets are being provided. Those can be taken into consideration. This looks like this. This can be taken into considerations and do the heat load calculation at the desired data. But limitation of this manual calculations are the storage effect. That's what I explained you during the discussion on the building envelope. So that is missing in this calculation. Otherwise, this can be used, and majority of the industry is using this widely to save their time and probably money. Okay, these are few screenshot of that, how it looks, how to enter data. If you have any concern doing that, please do connect with me. I can help you deriving that data and adding that data for the heat load calculation. So this is what the point I was discussing about the storage effect. The morning loads are different, building heat release rates are different. So this storage effect is missing in the manual calculation, and due to that, we are missing on the precisely load calculation. For that, we have different method that we'll discuss in the future side. So these are the equipment schedules for different, I would say, different areas or different things. When it comes to computerized calculation, there are different software. Have hourly analysis program is one of the popular software. There are software like Train, IES, Integrated Environment Solutions, and many more, maybe Leap softwares and all. So those can be taken in considerations when we do the heat load calculation. If you see that there are different tabs, and in that we can add the data and do the heat load calculation. So these are few snapshot of that calculation. In that, the benefit is you can calculate load 24 by 7, 365 days. So whatever data every single day you can, if you want, you can go and analyze that data, and based on that you can design your system. But once we do the heat load calculation, we will have to find out the possibilities of heat load calculations. Once we have those loads in hand, we should check or reiterate every single loads, recheck every single loads. Why I am insisting on concentrating on this specific thing? Because the load is going to stay for next 50 years with the building. If we do any mistake calculating the load, probably it will trouble that building for 50 years. And as we are having motto of becoming carbon neutral by 2070, it is my humble request that whenever we do any heat load calculation, has to be checked 2, 3, 4 times before being executed. Now these are the once we do heat load calculations, these are the factors to make human thermal comfort. I mean, if somebody wants to feel very much comfortable in environment, so clothing, air movement, air temperature, humidity, metabolism of that person, and radiant temperature. So these are the parameters responsible to make that human comfortable in desired ambience. And because of this feeling, we normally feel that one person is comfortable in certain environment, and in same environment other person is not comfortable. This happens because of his clothing, or maybe metabolism, maybe other components change in this, maybe air movement or temperature. But as an engineer, these are the four parameters. We can't control anybody's metabolism, okay? Or we can't ask some people to wear this specific kind of a clothes. So as an engineer, we have these parameters in our hand when we do or design any air conditioning system, which is air movement, temperature, humidity, and radiant temperature. Normally, whenever you have heard about the air conditioning system, you must have only three components. One is air movement, air temperatures, and humidity. But why we have added radiant temperature inside that? Okay, everyone is now driving a car, or we are traveling through cars majority of the time. If you have observed that even the car indoor temperature is comfortable, still we feel that it is very hot inside the car at certain specific point where there is a direct sun coming from ambient. So this is happening because of the radiant load of that you know glass. And here, when we design the radiant cooling system, there we are going to utilize this temperature to make human more comfortable. Or just through an example, like I explained in our initial discussions about the caves and forts. If you see, majority of the time when we use or visit this kind of places, majority of the humans are comfortable inside that. And why it feels? It is because of the radiant temperature. And that's what we are going to do in this technology. Okay. Uh, we will calculate the radiant load. Before that, we need to understand there are different kind of radiant cooling systems. So there are two different kind of radiant cooling systems. In that, one is the high mass. High mass is basically a system where there is radiant cooling system installed inside the structure. If you see in this, there is a huge structure, and the radiant cooling system or radiant cooling pipes are installed inside the structure, and it is being removed from that place. So this is one system where there is it is called as high mass. There is one more system, we call it as a low mass. Low mass is a system where there are some metals or gypsum panels, and from there we are removing the heat from the conditioned area. So due to this name, high mass, the mass of the building is high, and because of that terminology, it is being called as in high mass. And here the mass is low, and due to that, this system is being called as in low mass. So what is the difference between these two, high mass and low mass? So it is having its own advantages and disadvantages that we will discuss now. Like high mass buildings are basically a building where the mass is very high. It means it will take more time to get cool, but once it is cool, it will take higher time to rise the temperature. So these kind of buildings can be constructed where there is a electricity tariff differences benefit, because in few areas also nowadays it is gone, but few areas the daytime tariff is very high compared to night time. So daytime we can use that mass for cooling, okay, without adding any additional, without removing the heat. And night time we can make those buildings ready to use daytime at very low cost, because the tariff is very low in the night. So one was the response time. Similarly, low mass systems are very responsive, very fast responsive. It gets cool faster. It reduces temperature very fast and increase also very fast. That was one difference. The other is the cost of high mass is very low, because it is being embedded in the system, and because of that, you know, embedding in the system, it cost of the system is very low. Vis-a-vis the low mass systems are made up of panel, and we'll have to have support system in that, and the panels are needs to be maintained for corrosion and other things. The cost of this system is very high. But in high mass, you won't get the material choice. Like architects want to design building the way they want, like finishes and all. So that concept or that benefit will get in low mass. So these were the few differences. This system selection depends on the user, the price of the project, the cost of air conditioning system, and other aspects. So when we design the radiant cooling system, so we will have to consider few aspects when it comes to design the system. Like what is the pipe diameter, how much spacing is being maintained inside that, and what is the slab thickness, and indoor temperatures are being maintained. So these are the parameters when it goes to calculation. Once we have heat load, indoor load, we will have to play with this parameter so that we can maintain the specific temperature. So these are the few, I would say, things I have done to understand someone. Like if we have room temperature of say 29 degree and slab temperature is 20 degree, it can carry maximum heat of say 100 watt per square meter. I have just reduced temperature slowly. You can see the effect of system is getting reduced. So this is just to throw the higher the difference between the system, the slab and a radiant panel and the room, we are going to get more benefit out of it. The moment we are reducing the difference, the benefit is less. So this will help when we select any system or radiant cooling system configuration like pipes and all. Selecting the chill water temperature of radiant cooling system. For that, what I did is I have done some analysis with the CFD so that I can show it to you for various temperature. Like this is the analysis where we have done the slab thickness is 300 mm, the water temperature is 17 mm. Okay, And with that, you can try like the lower temperature, the best surface temperature that I'm getting inside the conditioned area is 21.15. Just to show what is the temperature is varying in different conditions. And now I'll show you some different conditions. So this was 350 slab versus 17 So this is 200 and 50 slab with 15 sorry 15 degrees Celsius temperature, but insulation on the top. So how temperature is varying? This side, this concept is same, but the insulation on the lower side. So how slab is being behaving? So this is the neutral where you know uh, the analysis is being done, how it performs when there are multiple pipes installed. So once we come to know that what is surface temperature and load is being maintained, we can calculate the exact heat absorbed through the surface, and based on that we can select the spacing. Now you see that there is a certain spacing. If we'll have to increase the heat absorption of the slab, then it means we'll have to reduce the either temperature or maybe spacing or maybe increase the diameter. So these are the parameters which we can change and see the calculations. So normally we don't have to do CFD every time. This CFD analysis I have added to get feel how system is behaving when the parameters changing in the system. So there are few manual methods which can be used to calculate the performance of the systems. Once we know how much load is being calculated to radiant, um, we can calculate the actual remaining load through the system. Till this point, I think you must have understood that this system, when it comes to very high temperature like 23.4, 21 degree, it means this system is only and only meant to cater the sensible load, not for the latent load. So whatever balance sensible load and the latent load, for that we will have to select a different system. Okay, total heat load minus radiant cooling system load is equivalent to balanced load, and balanced load can be catered through the conventional air conditioning system. This slide I was explaining, you don't have to do CFD every time. There is simple formula of this, the surface temperature and nominal room temperature. With this formula, you can simply calculate. So these are the some calculations are shown in this. So with these calculations from the manufacturer to manufacturer, these are different graphs available for different spacing, different temperatures, different diameters. So those charts can be just pulled down from the manufacturer, and based on that we can calculate how much heat is being transferred through this temperature difference or through the radiation. These are the heat load calculations. From there, the sensible load and latent load can be bifurcated, and from there we can calculate the balanced load. This slide is being added just to show an idea how the actual calculations are being made. Okay. Once we do that, balance sensible load, and from that balance sensible load by using MCP delta T formula, we can calculate mass, which is air flow rate, and based on that mass we can select the air flow rate for the HU, and only balanced load we can handle through this system, so we don't have to have so big ducts and all. Now when it comes to radiant cooling system, there are few components, like one is the floor pipes, second point is where the air is water is being distributed through this channel part. Three is room sensor, like we'll have to see the what room temperatures are being maintained. Four is the system controller, where it is talking to manifold and room sensors and outdoor air temperature sensors and the control valves. 9 is the circulation, water circulation temperature or walls. I mean, either way it can be used, but these are the basic components used in any radiant cooling system. Now I explained like it can be installed in many ways. Slab is one of them. It can be even installed in screed. If building is ready, then even it can be installed in the last layer of PCC where we call it plaster. So there are very thin pipes available in the market of say 13 or 6 diameter. Those also can be used to install the radiant cooling system. Similarly, in the floors, it can be either installed in grade, slab, or PCC, or maybe screed just before the tile. So either way, if building is completed, building is half constructed, in any ways, we can do any configuration. So now I'll show you some, typical, you know, places where it can be installed, what kind of finish we can have. It can be installed on grade slab, post that we can have insulation, maybe wire mesh, then PEX piping, the structural slab, and whatever finish we want, like flooring slabs and all be done. Similarly, it can be installed. This is the example of deck slab where the radiant is installed. These are the chilled ceilings or panel. It looks like this when we use the chilled ceilings or panels. So these are the typical images of panels where architects get a benefit of selecting the design as per his choice, and based on that also we can calculate the performance. These are the typical installations of the chilled ceiling panels. Now, when it comes to these are the few installations where you see that how the ultimate outcome has came with the radiant cooling system. This is the manifold box I was explaining where the distribution is happening. Like this is the detail overview of that manifold box, how it looks. Radiant cooling system main component is the control system, because if we won't control this precisely, then there are chances that condensation may occur. Because in India, if you see that the system is not so popular because of the mistake has been done by somebody while designing one of the first project in India. So there they have selected conventional chillers and the temperatures were very low, and because of that there was huge condensation on the slab. Those has to be selected properly, has to be controlled properly before using the radiant cooling system. These are a few examples of pre-assembled manifolds. This is the one of the method where piping is installed. This is the example of using the PEX piping with desired mats. There are few mats available where just we'll have to install or add the pipes and equal spacing can be generated. This is the manifold installation at the site. Typical, even this can be installed in different modules also. We can create modules somewhere else and just bring it at one place and keep on the terrace and just install it. So this is the thing I was explaining, that why operative temperature or radiant temperatures are important, because it will change the perception of human being sitting in the same environment, like I explained about the car. So if we have room temperature of say 78 Fahrenheit or 24.6 degrees Celsius, or at the surface temperature of 18.9, so AUST is 25.5 and mean radiant temperature is 22.2. So with that, operative temperatures become 24 degrees. So this is the way the operative temperature is calculated, and our body normally responds to these temperatures. When it comes to application, it can be installed in any thermal comfort or any comfortable environment, like say offices, maybe industrial areas, hospitals, malls, and uh, residential bungalows, or maybe stadiums also. This is one of the stadium, airport, and other things. Now, why to use the radiant cooling system? The way I started my discussion mentioning that now, as India, we are trying to save the energy to become carbon neutral. So, our past experience says that when we do the radiant cooling system, and when it compares with the conventional, we are saving almost 35 to 40% energy when it comes to power consumption of the building. And we know that we are one of the responsible user of the building, because 60% of the power is being consumed by air conditioning system, and if we reduce 40% into that, it is major chunk of the power consumption in the building. With saving energy, it is giving us more comfortable environment like caves and other areas. So we are getting more comfort with lesser energy, should be our motto in designing future buildings. So this is the Bangkok airports where the radiant cooling system is installed. So thank you. So this is what my discussion was. I think I'll stop sharing. If we have any question, we can discuss those. Yeah, I think nobody has posted any question, but if we have, we can
Hello,
discuss.
am I audible?
Yes, sir.
This is Professor Nilesh Gaikwad. So,
Yes, sir.
like you said, that in terms of energy, it can save around 30 to 40% of energy. But
Right.
in terms of capital cost, how much extra it takes as compared to conventional air conditioning system
It
in
is,
percentage, maybe?
yeah, it is costlier when the buildings are smaller. Like if we have 1 lakh square foot area, it is say 25% costlier. But if the building size is beyond 2 lakh square feet, then it is cheaper. Like I have designed one project in Pune called Mahindra Tower, which is in Sakan. So there the area is 2,50,000 square feet. So when we did this analysis before using the system, it was cheaper to use radiant than the conventional system. So it depends on the size of the project. But smaller project, yes, it is costlier around say 20-25%. But that recovery is not more than 2 years.
Hi, sir. Professor Abhijit Kore here.
Yes, sir.
Hello.
Yes,
Am I
sir.
audible?
Yeah.
Sir, there is one more question. Right now, sir is asking about the initial cost. But what about the operational or maintenance cost?
Okay. See, the maintenance cost of this system is very low, because what I started, how I started explaining is we need a very less air transfer unit or very small air transfer unit for the balance load. Nowadays, what is happening is in conventional system we have hundreds of AHU, and it gets failed because there is corrosion, erosion happening on the metal. And when it comes to slab installed piping, the guarantee of piping is for 20 years, and there are very less moving parts like pumps only. So maintenance cost is very low compared to the conventional systems.
But in this case, also corrosion, there is a possibility of corrosion.
No, I mean, to PEX is a polyurethane material. It won't get corrode or erode.
Okay. Okay.
So corrosive component, what are our corrosive component? This is very small AHU, which is almost 30% of the conventional. If we have conventionally say 10 AHU, in this kind of projects only 3 AHUs are required. I have used a radiant cooling
Okay.
system for Mahindra Tower where only 2 lakh 50,000 square foot area is being conditioned only with the 3 AHUs. So
Okay.
less moving component, and because of that, there are less chances to get corrode or erode.
Mhm.
Aditi here. Hello.
Yes, ma'am.
Sir, the water qualities matter for that? The what you are saying, the corrosion or erosion.
Yeah, in any process, in any air conditioning system, quality, water quality does matter. Because nowadays many, you know, um, system has came to maintain this water quality. Like we have cooling tower water treatments available to treat that water. We have many systems like degasser is there to remove oxygen from the water so that there will not be erosion or erosion in the system. About the air we can't have, I mean, control on corrosion on erosion.
Okay. So the mostly the soft water is used for these systems or any specific
Any
other
in
one.
any air conditioning system, it is recommended to use the soft water because we have opened up many old pipes or old installation, I would say. There, because of this water quality, the corrosion has happened. Corrosion is not only leading to, I would say, performance of the system, but overall it is getting higher power consumptions and many other disadvantages. So yes, coming back to your question, yes, water quality is important.
Okay. Thank you, sir.
Okay, thank you very much, sir. Is there any question? Okay. Uh, Sir, Chetan, sir, the president of Shri Pune chapter is along with us, sir. Sir, are you address some to the participants, sir? Chetan, sir.
So, means I like to thank first of all Amit Gulawade ji for giving taking out time and giving this session. And I was attended more than half an hour. I was not able to join from the beginning, but it was really a good session. And uh, thank you very much to all the delegates for attending this session. I guess tomorrow is going to be one more, na sir?
I think tomorrow and day after.
Yes, sir. Day after
Yeah,
tomorrow also.
yeah, that's tomorrow also. So see you tomorrow also, all of you. Thank you
Okay.
very much.
Thank you, Chetan, sir. Now the conclusion ceremony is here. The head of the department, mechanical engineering, Power sir, is here also.
Okay.
Sir, please, hmm, please conclude, sir.
Yes, yes, yes. Good evening, sir. So our today's respected speaker, Mr. Amit Gulawade sir is here. Our honorable CEO, principal, management members, and Ishri Pune chapter representatives are here. Also, dear faculty members and students. So, on behalf of our Jain College of Engineering and the Department of Mechanical Engineering, I sincerely thank you all for being part of this day two session. And this our online FDP is basically on advancement in HVAC and R. So today's session is on modern approaches and application of radiant cooling system, which was extremely insightful and relevant, sir. So you beautifully explain the practical aspect and real life application and the future scope of this radiant cooling system, which will surely help for our faculty as well as our student to bridge the gap between the theory and industry practices. So I would like to express my heartfelt gratitude to our Amit sir for sharing your valuable expertise with us. I also extend my gratitude to Ishri Pune chapter for sponsoring and supporting this FDP. Also to our honorable CEO, principal, and management for their constant encouragement and vision toward this FDP and quality education. So, dear participants, I hope you found today's session enriching and motivating. So, I request you to all to actively participate in the upcoming sessions also and make the best use of this great learning opportunity. So with this, I formally conclude this day two session of our FDP. Thank you all once again for your valuable time and the presence. Thank you.
Thank you, everyone.
Thank you, everyone. Thank you.